Thank you so much for coming today. My name is Anton. I'm a Principal Solutions Architect for serverless stuff at AWS. And today we'll be talking about a pretty fascinating topic, how to improve throughput and monitoring of serverless streaming workloads. So quick show of hands. How many of you already have a streaming workload implemented with serverless? Kafka, Lambda, Kinesis? Okay, some of you. How many of you are planning to implement it? Okay, also some hands. Okay. So, a couple of admin things. Feel free to take pictures of the slides, but you don't really need to, because in about 59 minutes, towards the end of this presentation, you will see a giant QR code that will give you links to everything you're going to see in the next 60 minutes, including these slides. So you'll have these slides in about 59 minutes, right? But feel free to take pictures if you want. All right, without further ado, let's talk about cars, right? Imagine you're a world-famous racer, right? And you're picking your new car. What do you think are two most important metrics when you're choosing your car? Now, you might have different answers in mind, but from my perspective, one of the metrics is what's the maximum speed of your car, and the second is how fast you can get to that maximum speed. If we chart that, you will see something like this, right? So you start at 0. This is because you're not driving just yet. You accelerate. You reach that maximum speed. And from that point on, your maximum speed continues, right? Now, I'm using this example because it's really easy to digest. But it's not just about kilometers or miles per hour. It's also about messages per second or gigabytes per second. So when you think about throughput, right, this analogy is actually really helpful. Let's continue talking about cars. Cars are pretty sophisticated today. They are packed with various sensors, and they measure things all the time. And all of those metrics are emitted continuously to some sort of the mothership system, some system that ingests that and provides insights, right? Now, this picture looks pretty simple because I only have 4 sensors, right, and 1 car. But imagine something like this. Hundreds, thousands, tens of thousands of cars and millions of those sensors continuously emitting data, right? And you have a lot of data flowing into your system. So you need to ingest that data, and you need to process that data. We'll be talking about both of these things today, right? So in order to achieve that, you need something that we call a data stream. And this is a generic conceptual name. Now, data stream is a component in your architecture that actually allows you to achieve this use case efficiently. Ingest huge volumes of data and process that data efficiently in your cloud applications. There are several common use cases for streaming workloads. For example, application click streams, right? When your users are using your application, you want to know what they're doing. So all of that data is flowing from your applications to your system for analysis, and you improve user experience. Connected devices, cars, factories, TV sets, right? This is our daily life. Financial data, like stock tickers, for example, right, or transactional data. Real-time anomaly and fraud detection. If someone is using your credit card in a different country, you probably want to know about it right away, right? And there are millions, if not billions, of transactions going on all the time. Now, few characteristics of streaming workloads include things like high volume, right? Usually it's gigabytes, terabytes, sometimes petabytes of data flowing through your system. So it's a very high volume data. It's continuous data. It's not something that happened and then you wait for a few minutes for the next thing. It's a lot of continuously flowing data. In vast majority of the use cases that I've seen, it's ordered. So order matters, right? If you're going through a list of transactions, you want to know what was the order of those transactions. Time sensitive. If you're getting information about that transaction, like, 2 days later, probably it's not that important. You want to get this information as soon as possible. And the last one is spiky. Spiky is something that we'll be talking about quite a lot today. Now, this is a consistent workload. The blue line represents published records per second. Now, if I'm planning my consumption side of it, it would probably look something like that. That's the capacity I need to provision to consume those workloads. Consistent or flat workloads, they're pretty easy, right? The problem starts here. If this is what my workload looks like, if it's super spiky, Now, there are two general approaches and everything in between. You can either provision a little bit less, but then you might have a growing backlog of messages and sometimes delayed processing because it takes time to recover from those spikes. Or you can go into the opposite direction. You can over-provision. And in this case, your workload will handle incoming messages perfectly fine, but over-provisioning can actually mean you're overpaying for some period of time, right? It can get expensive. Now, with traditional server-full, right, infrastructure-based data processing, changing that line, moving that around, basically rescaling, can be hard, right? Because you need to provision that infrastructure and deprovision it. So today, we'll be talking about serverless streaming on AWS, right? And I will show you how serverless actually helps to address that specific use case. So remember that spiky chart? Towards the end of my slides, I will show you how that is handled with serverless. All right, our journey for today. We'll talk about concurrency. If you're talking about serverless data processing, you do need to have at least basic understanding of Lambda concurrency. We'll spend about 2 minutes talking about what that is. We'll talk about event source mappings, right? That's the component that actually helps you to get data from Kafka or Kinesis and process it efficiently in serverless world. We'll talk about techniques that are common to any type of event source mapping, basically common techniques regardless where your data is coming from. And then we'll talk about some ESM-specific techniques. So what do you do if your data is coming from Kafka or from Kinesis or whatever? We'll talk about some new capabilities that we've announced literally I think about 3 or 4 days ago, right? I'll show you some of that. And I want you to wrap up and go home with action items. So towards the end, like I promised, you will have a list of actionable things to work with. Let's dive deeper. So the consumer of the data is Lambda service. It's a serverless compute service, right, where you upload your code, and that code is executed as a result of data or requests flowing in. How many of you are using Lambda today? OK, quite a lot. Awesome. Guilty as charged. Let's spend a couple of minutes talking about Lambda concurrency. Now, let's imagine you have a request, a single request flowing in. So what will happen at this point is Lambda will create an execution environment for you. And you can think of that execution environment as a micro VM, right? That's the term we usually use, commonly use, not an official term, but we do use it because that's what it is. And that execution environment will run your code to process that data. Now, once processing has completed, we'll not shut down that execution environment just yet. We will keep it alive for some period of time. Why? Well, because you might have invoke 2 coming in, right? You might have the next set of data flowing in. And it's much more efficient to reuse existing execution environments than create new ones. So the second invoke will be processed by the same execution environment. Now things are getting a little bit more interesting. The third invoke is coming in during the second invoke. Second invoke is still being processed, but you got the third one going in. What will happen in this case? Well, Lambda will scale. It will create another execution environment to process the third invoke. And we will also keep it alive for some period of time. Let's make it a little bit more interesting. We're at this point in time, right? There is invoke number 4 coming in. Show of hands, how many of you think that Lambda will create another execution environment at this point? Good, it will not, because it will reuse available execution environment. That's the beauty of Lambda. It knows how to reuse those execution environments, and you're only paying for the time that those execution environments are actually processing something. So not for the gray area, just for the blue area. Let's make it a little bit more advanced. 2 invokes are coming at this point in time, right? 2 execution environments will be reused. 3 invokes coming at this point in time. What's going to happen? How many of you think that new execution environment will be created? The right answer is yes. A new execution environment will be created because I got 3 invokes to handle. The hardest of them all, we're at this point in time, and I got 4 new invokes flowing in. What's going to happen? Well, 4 new execution environments will be created because I need to scale. This is what we call Lambda function concurrency. So essentially, the number of concurrently running execution environments is the metric that we call Lambda concurrency. And the more concurrency you have, the more parallel processing your Lambda provides you for streaming workloads. Now the question is, right, now that we understand what concurrency is, how fast can that concurrency scale, right? Remember, your car, the maximum speed and how fast you can get to that maximum speed? And the answer is quite fast, right? So you start with up to 1,000 execution environments right away at time equals 0. And then every 10 seconds, we will give you up to 1,000 additional execution environments. So looking at this realistically, this is from CloudWatch. This is Lambda scaling from nothing to 16K execution environments in 3 minutes. Now, 16K execution environments, that can be almost 100,000 virtual CPUs, right? That's larger than some clusters at big universities, right? So Lambda can scale very efficiently. Now that we know that, how do we monitor that? Because this session is also about monitoring. Lambda emits a bunch of metrics automatically, right? You don't need to do anything. Those metrics are emitted out of the box to CloudWatch metrics. And the important thing is those metrics correlate. So for example, you can see here that the duration of my function is high, right? As a result, I need more concurrent execution. So if my function is slow, I need more instances to process the data. But if my function is fast, duration is dropping, I need less concurrency. Make sense? Okay, let's continue. So we talked about Lambda. Let's also talk about event sources, right? So you understand how concurrency works, but how does data from event sources like Kafka, Kinesis, etc., actually reaches the Lambda function? Because all of those event sources, they are what we call polling event sources. They are not triggering Lambda, right? They're not invoking, making HTTP requests. You need to poll. SQS is one of those polling event sources as well. So there's an internal component, right, in Lambda, a component that if you're using Lambda for data streaming, you all use and familiar with, called event source mapping, aka pollers, aka many things. The official name is event source mapping. Okay, how many of you are using ESMs today? Okay, quite a few. What I want to do today is let's actually dive deeper into every single stage of ESM, what's happening internally. If you look at this, regardless of what's the type of ESM, basically if it's Kafka or SQS or whatever, there are 4 steps. Polling, that's actually getting the data. Filtering, because you might not need all the data. Batching, and actually processing, invoking the Lambda function. So with this in mind, let's talk about common techniques to optimize your throughput. Techniques that are relevant regardless of what event source type do you use. Now, I'll use a bunch of visualizations to actually show what's going on. And this is my most basic data stream processing, right? Streaming data processing. I got new messages incoming all the time, and they're being processed one by one, right? Processing takes 1 unit of time, whatever that is. Second doesn't really matter, from T0 to T1. Now, how can I improve the throughput of this data processing? We started with concurrency, right? So obviously, that's going to be our first answer. You can increase the concurrency, right? You can increase the number of concurrent sandboxes, execution environments that are processing the data. How do you do that? The best part is you actually don't really need to do this manually. It will happen automatically. The Lambda will detect that you have a lot of messages or records to process, offset lag, right? And it will increase that concurrency automatically for you. We'll talk about how fast this is happening and what's the efficient way of doing that. But basically, increasing concurrency from 1 to 4, we just improve the throughput by a factor of x4. Let's talk about another technique. Before I tell you about a few things that Lambda can do for you, right? I want to emphasize that a big player in your throughput is actually your code. If you improve the efficiency of your code, you can process data faster, right, and increase the throughput. So on this example, I've decreased the processing time by about 50%, right? How can you do that? Well, obviously, you can see how you can optimize your code. You can process data in parallel in your code, not one by one, but in parallel, right, using threads, for example. But you can also increase the memory allocation for your function, which will grant your function more CPU. Right? With having more CPU, your function can process data faster. So the second technique is optimize the duration of your function. And with this optimization, we're at x8. Let's see what else. Filtering. This is something I see super commonly, right? And I'll show you some data points in a few minutes, right? But you don't necessarily have to process every single record you receive, right? And one school is saying, one technique is, I'll just filter out the stuff that I don't need in my code, right? But Lambda can actually do that for you. You can define patterns, as you will see, to filter things out. So if you're processing only half of the messages that you're receiving, you just improved your throughput by a factor of x16. And the last technique that is common to all the event sources is batching. You don't have to process those messages one by one. In reality, we see that it's most commonly the most inefficient way of processing data. You can process those messages in batches, right? And this is also one of the capabilities that you have to batch those messages before you process them. So here we're improving our throughput by about x32, okay? Let's summarize these few points. So the first one is parallelized data processing, right? The more parallel processing you have, the higher your throughput is, right? You can parallelize data processing by using, essentially Lambda concurrency. You can also parallelize data processing within your function code. You will see a blog link that talks about that in detail towards the end of the session, right? But parallelization helps you to improve the throughput. The other technique is reduce processing duration, right? You can allocate more memory to your function, which will allocate more CPU. You can look into your code and essentially optimize it, right? And see where you can, how you can decrease the duration. I've seen customers that were extremely latency sensitive, and they went as far as rewrote their functions to languages like Rust and Go. Right? Now, I'm not saying everyone should do that, obviously not, right? But that helped them to improve the throughput because they were extremely sensitive to latency and throughput. Filter irrelevant messages out. I will show you how to achieve that in a moment. And the last one, batch messages. Do not process them one by one. Evaluate what's the batch size that you need, right? And process those messages in batches. Now that you know what you need to do, let's actually see how you can do that. So the first one is, how do I actually decide how many messages I'm putting into the batch, right? We have a property at event source mapping called batch window. The property essentially defines whether the ESM will use short polling, meaning I'll get to that event source, I'll take whatever is available right now, I will not wait, and I will immediately process that, right? Or long polling. I'll connect to that event source, and I'll wait for 10 seconds. I'll aggregate messages during those 10 seconds, right? And then I will invoke the function. So the small batch window implies you will have more invocations, but smaller batches, right? Higher batch window, and this can be up to 5 minutes, implies you will have less invocations, which means it's also going to be cheaper, right? But you will have larger batches, right? How do you know which one to use, right? Unfortunately, there is no one standard golden answer for everything. You experiment. You try that on your specific workload, and you tune that system to the nature of your workload. The next one is filtering. So this is an example of how I can filter data out using code. This is a Node.js JavaScript snippet from the Lambda function. I can use this code to essentially just ignore messages that I need to process. But what it actually means that for those redundant messages, my functions are still being invoked, and I'm still being charged for those invocations, right? The alternative is to set the filter criteria on the ESM. Right? You can have exactly the same filtering criteria, but as a configuration of the ESM. As a result, those messages will never even reach your Lambda functions. You're not paying for it. Your throughput is higher. I want to show you a real example, right, that we're using when we're talking about this technique. So imagine this use case, 10K IoT sensors, a little less than 500 million messages a month, right? And only about 2.2% of messages result in action. Now, you can see the difference of the total number of messages to process without filtering and with filtering, right? It's quite stark, right? It's almost 500 million versus 10 million. That's a lot. And the cost just for request, just for invocation, is $90 versus $2. If you look at the milliseconds, the total time to process this data, this is 25 million versus 3 million. And if you look at the cost, it's $200 versus $15. Now, this is a real example from the field, okay? What it actually means, 92% cost reduction by filtering stuff in the ESM instead of filtering that in code. Now, I'll be the first one to acknowledge this is quite an extreme example, but it is real, right? You might get to lower numbers, but you know what? Even 30% is still amazing number, right, when it comes to cost reductions. The next thing is batching. This one is quite simple. It's literally a configuration property on the event source. You define what's the maximum batch size that your function is capable to process. Depending on the event source type, this can be anything from 1 to 10,000. Again, how do you know the right number? Experiment with your specific workload. Try to increase it and see the throughput, right? Try to decrease it. You do need to experiment because every workload is a little bit different. And the last part is, actually invoking the Lambda function. You filtered messages, batched them. Now you need to invoke the Lambda function. And it's not you that need to invoke the Lambda functions, it's the ESM. So ESM will invoke your Lambda functions when one of these three conditions are met. The first one is the batching window has elapsed. So if you define your batch window as 10 seconds, right, when the batching window of 10 seconds has elapsed, right, doesn't matter how many messages ESM has accumulated so far, it will invoke your Lambda function. And it's not a single thread ESM. You have multiple of those ESM. You will see that, right? Multiple of those pollers working at the same time. The second condition, the batch is full, right? So if the batch that is used to invoke your Lambda function is full, right, ESM will not wait for that batching window to elapse because there's no reason to do that. It will invoke your function right away, right? So we're trying to be very efficient. And the third one is batch size is 6 megabytes, right? 6 megabytes, that's the maximum payload size for a Lambda function. So internally, we're monitoring how big is that batch. Once it starts to approach 6 megabytes, we will invoke your function. Now, once one of these conditions is met, the invocation will happen. Okay, make sense? How do you configure that? I've showed you some snippets from the console. This is what it looks like with infrastructure as code, right? Because obviously, everyone should be using infrastructure as code. Anyone here is not using infrastructure as code? Good, thank you, right? This is a Terraform example. You can do exactly the same thing with CDK, SAM, CloudFormation, whatever your infrastructure as code flavor is, right? It's literally just a configuration that you can use when you're tuning your system. So now that we've discussed methods that are common regardless what ESM type you use, let's talk a little bit about things which are specific to some event sources, okay? So when you talk about data streaming, it's common to talk in the notion of producers that push messages to the data stream and consumers that consume those messages from the event stream. If you're using Kafka or you're using Kinesis, sometimes this terminology is even used with SQS, right? It's pretty common terms. I will be using these terms for the remainder of this session. Now, two main players today will be Kinesis and Kafka. And let's start with Kinesis. So Kinesis data stream, it's a serverless service, right? There's no infrastructure for you to maintain, right? And it gives you the notion of shards. So you maintain, you scale your Kinesis stream by introducing more shards. Shards define your throughput capacity, as you will see. Now, Kinesis supports two modes. It can be either a fully automated mode where we, AWS, Kinesis service, will manage the number of shards for you automatically. Or you can decide that, you know what, nope, I want to do manual management. I will be the one deciding how many shards do I need. But that's essentially the only kind of thing that you need to manage. Like, again, there's no infrastructure, clusters, any of those kind for you to manage. Kafka, on the other hand, is a little bit more sophisticated. Now, it does come with some cluster management. You might be using Kafka that you run on premises or in cloud yourself. You might be using Amazon MSK, Managed Streaming for Apache Kafka. That's our managed version of Kafka. Doesn't really matter. We connect to all of them. Confluent, name it, right? We connect to all of them, right? But regardless of what type of Kafka you use, you have a notion of Kafka cluster, right? And those clusters come with brokers. Now, a little analogy, right? Kinesis streams are very similar to Kafka topics. And those shards on the Kinesis side, they are similar to partitions on the Kafka side. So it's conceptually similar, different terminology. There are some differences, as you will see, right? But Kafka essentially means you do need to be aware of the cluster, okay? I got the slide here to compare the terminology, right? Once you download the slides in about 35 minutes, right? You can see here, and terms like records, events, messages, we use them a lot interchangeably because, depending on what event source you use, right, they have their own terminology, right? But for processing perspective, it's just a chunk of data that you need to process, okay? So let's start by talking about how those partitions and shards work a little bit more in details, right? So Kinesis and Kafka, they split data into partitions or shards for improved scalability and improved throughput. Producers, they put new records into a particular partition or shard, and each partition and shard always contains an ordered set of records. Remember, ordered, right? Now, new records are always added at the front of the partition, right? So older messages, they're not deleted. If you're using SQS, you know that once you process data, you need to delete it. With streaming data sources like Kafka and Kinesis, you don't delete the data. It will just age out over time by itself, okay? How do producers know which partition to use? This is done by using partition keys. Right, the partition key determines which partition your record will be stored at. So there's a hash function, doesn't matter which one. There's a hash function that takes the partition key, hashes that. According to the result, it will put those messages into one of the partitions. If you do not specify partition key explicitly, one will be auto-generated. If you have only one partition, regardless of the partition key, all the messages will go to that partition. So by using different partition keys, essentially producers know how to push those messages or records to different partitions or different shards. Let's talk a little bit more in detail about Kinesis, right? Like I've already mentioned that Kinesis comes in two flavors. You can manage the number of shards yourself. You can delegate that to AWS. Now, why is that important? So Kinesis data stream, like we mentioned, it's a collection of shards that contain data records, and each shard provides a fixed unit of throughput capacity, okay? Kinesis consumers, they read from all the shards in the stream, and consuming Kinesis stream can actually be done in two modes. The standard or default mode, right, we call it shared throughput. Now, when you're using this shared throughput mode, right, consumers are polling data from Kinesis. They're literally connecting to Kinesis and polling data over HTTP from Kinesis. Now, your throughput is 5 reads per second and about 2 megabytes per second, right, that you can get. Now, the throughput is shared across up to 5 different consumers. In Lambda world, right, this usually would be 5 different Lambda functions. It's not, different, it's not ESM of the same function, it's different functions consuming that, right? And the latency that you can expect is about 200 milliseconds, right? Now, as the number of consumers increases, you can also see that latency going up a little bit, right? But the baseline, this is what you can expect. So essentially, mind the number of consumers you have getting data from that shard. Now, if your workload is very latency sensitive and it requires very high read throughput with low latency, you can use what we call enhanced fanout or EFO mode. Now, in this mode, the consumption is kind of flipped, right? Instead of ESM polling data from Kinesis, Kinesis pushes data to ESM, right? So it's a push model. That's why it's significantly faster, okay? So each consumer gets dedicated 2 megabytes per second throughput, and Kinesis uses HTTP2-based protocol to send data to those consumers. The latency is as low as 70 milliseconds, so it's significantly lower, which means you can also improve the throughput, right? EFO consumers, they do not contend with standard consumers, which is great, right? You don't have that noisy neighbor problem. And you can have up to 20 EFO consumers per stream, not per shard, per stream, right? Lambda ASM supports both, right? So it's up to you to decide which mode you want to use. We support both. How does it scale? So when you enable event source mapping for Kinesis Stream, under the hood, we will create a number of pollers, right? It's a term that we use internally, but it's also a term that we use quite a lot in our blogs or when discussing this with people, because it's the name is pretty self-explanatory, right? Intuitive. So we use this term pollers, right? Each poller will do polling, obviously, filtering, batching, and then invoking the Lambda functions. Now, the number of concurrent execution environments that you have processing the data by default will be equal to the number of shards. Okay, so I got 2 shards, I got 2 lambdas over there, right? That's your concurrency. Okay, so your concurrency is restricted by the number of shards. That's the important thing to know when you're evaluating the throughput. Now, Lambda ASM will poll those shards at rate about once per second, right? And the big question is, right, the topic of this discussion, so how do you actually improve the throughput? Now, we already know that the throughput is constrained by the number of shards. So one logical thing to do is, let's actually add some more shards, right? We can increase the number of shards in the stream. And once we have more shards, we will have higher concurrency, which means higher parallelization, right? Additional execution environments. And the processing, the overall throughput, will also increase as well. Now, adding new shards is a great way to improve throughput if you're hitting your bottlenecks on the Kinesis side, right? But if your bottleneck is actually on the other side, for example, your functions is just slow, right? And you currently do not have resources to optimize that. Your function takes, I don't know, 7 minutes to process a message for whatever reason, right? So Kinesis is not your bottleneck. Now, you can still increase that, the number of shards in Kinesis, but that would be an expensive solution because Kinesis billing is per shard, right? So what can you do in this scenario when, you can improve the throughput with Kinesis, but that's not where the bottleneck is. Now, in this scenario, Lambda provides you with additional way to improve parallelization. So by default, ASM creates a single Lambda execution environment per shard in the stream, like you see on the screen. But ASM also supports the configuration property called parallelization factor. And I think, based on the name, you already understand what exactly this is going to do. Now, you can configure parallelization factor anywhere from 1 to 10, right? 1 is the default. So let's see what happens when you configure it to 2. Well, essentially this. Now, every single poller will create 2 execution environments to process data concurrently. Now, as a result, the data stream is processed twice as fast, right? And it can be up to 10 times as fast without actually adding new shards. Filtering, batching, order, all of that is preserved. You're just getting higher concurrency. So this is a really convenient way to scale out your data processing on the consumer side, not necessarily on the data stream, but on the consumer side. Monitoring-wise, observability-wise, I've grayed out all the Lambda metrics that we've discussed previously. You have tons of metrics on the Kinesis side to monitor the performance of your stream. Things like number of put records and get record successes, incoming, outgoing records and bytes, iterator age millisecond, and you have a corresponding metric on the Lambda side. This is a great metric to understand how old are the messages, basically, if your function is processing data fast enough, right? Because if your function is not processing data fast enough, the iterator age is going to grow, as you can see on the diagrams up there. So all of those metrics allow you to have very efficient monitoring of the throughput of your end-to-end system. I have those questions here. I'm not going to go through every single one of those questions, but essentially, the most common question is, my iterator age is growing rapidly. Why? Right? And these are the questions that you can ask yourself to understand what's going on. Well, how many Lambda functions are subscribed? Maybe somehow you have 50 functions subscribed to the stream, and there's a contention going on, right? Do you have any errors, or do you have any throttles? Is there a large increase in incoming records or incoming bytes? So these are the most common questions that will tell you why your iterator age is growing. Like I said, you'll get these slides, you'll get all of these questions, and you can process them. Let's move to MSK and Apache Kafka. Let's switch gears a little bit. Now, like I've mentioned, you can host Kafka yourself. You can use managed Kafka, completely up to you, right? MSK is, like I mentioned, it's a fully managed service that we provide to run your Kafka workloads. We manage a lot of underneath, under the hood infrastructure for you. You just decide how much capacity you want, where you want to put those brokers, what's the capacity of brokers, memory, storage, etc. But we'll manage it for you. But let's look at the consumption side, right? Because this is what's interesting. So let's see how Lambda ESM scales when consuming from Kafka clusters. So when you initially create ESM for a Kafka cluster, we create a single polar for you, right? So this is the starting point. You just connected Lambda to Kafka. There is a single polar. Kafka polars are a little bit different. They can, out of the box, invoke multiple instances of Lambda functions. So essentially, a single polar, not limited to one concurrency, right? A single polar can have more than one concurrency. The number heavily depends on the number of messages, the backlog, etc. All of that is managed fully automatically for you. So that polar, like previously, it will poll, filter, batch, invoke. It will do all the magic, receive the records, and etc. And the order is obviously maintained at all point in time. Now, over time, based on the incoming workload, so we detect the increase in offset lag, in backlog, we detect that, and we will automatically scale up or down the number of polars, okay? This is, the sampling is done roughly every minute, so once a minute, we will see what's the, how many messages you have in the backlog, right? Do we need to increase the number of polars? Do we need to increase the processing speed? And if the lag is increasing, we'll actually start creating new polars. New polars imply higher concurrency because new polars will also create new Lambda execution environments, right? So, and this will grow until the number of execution environments match the number of partitions. Very similarly to the way it works for Kinesis, because we need to keep this processing ordered, right? We cannot just have, million execution environments processing 3 partitions, because this way we'll break the order. With Kafka and Kinesis, the order needs to be kept, right? So the total processing concurrency will scale up to the total number of partitions in the topic. Important note, while we sample those, while ESM samples those partitions, like I've mentioned, every minute, it can actually take more than a minute. It can take several minutes for the scaling to happen, right? So maybe you just had a tiny spike and there is no need to scale. Once we see some consistency in the increase, that's when we're going to scale and we're going to accommodate the backlog, as you will see. So let's take a look at the metrics. Similar to Kafka monitoring, right, from the observability perspective, you have those metrics, things like partition count, bytes in per second, bytes out per second. I highly recommend that you monitor that because this shows you how much data is getting into your Kafka, right, and how much data is being out of your Kafka. So how much data your ESM is actually pulling and processing. Right. On the Lambda side, you have all those standard throttles, duration, etc., and also offset lag. Now, one thing I want to mention here is do not confuse Kafka offset lag and Kinesis iterator age. They're used for the same purpose, but they show you different things. Offset lag shows you how many message records you're behind on, right? So offset lag of million means there are million records in your Kafka topic that were not processed just yet. Iterator age doesn't show the number of messages. It shows how old is the oldest message that you haven't processed yet. So they're used for very similar purposes, right? But they show you different things. And one more important thing I want to add here, and also relevant for both Kinesis and Kafka, is that the function duration is super important metric, right? That's how you know that your function is either slow or fast. But don't look at it in a vacuum. Always look at function duration, right, together with the batch size, okay? what can happen, because we're talking about scaling here, improving the throughput, right? Maybe your workload was pretty low, and the batch size, you've defined batch size maximum as 100, but you had about like 2 or 3 messages in the batch because your workload, it's middle of the night, right? No data is flowing through your system, right? And your function duration is also pretty low. Towards Black Friday kind of event, right, you're starting to see a huge increase in traffic, which means your batch size is now no longer 2 or 3 messages, it's 100 messages. So it kind of makes sense that your function duration is longer as well, right? So when you're looking at duration, always account for batch size as well, because your batch size might increase, tenfold, but duration would only double because you have parallelization within function as well, right? So those 2 metrics correlate, and take a look at both of them when you're monitoring your system. Now let's talk about some interesting new stuff. I've mentioned to you that we sample the offset lag about once a minute, and it takes several minutes to start scaling those polars, right? But what if your Kafka workload is super spiky, it's latency sensitive, right? And you want faster and more predictable performance. Basically, you cannot wait for 10 minutes, 15 minutes, whatever the number is, right? You want data to be processed much, much faster, and you're looking for predictable performance, something that you can predict, okay? So with that, I'm happy to tell you about the provision mode for Kafka ESM that we've introduced several days ago, okay? And the idea of the provision mode is you can configure a minimum and a maximum number of polars that are always on. Now, the minimal number of polars is always on, right? But it's also configurable how high that number of polars can go. So it's up to you to define that range. What I mean always on polars, think of it as a consumers, Kafka consumers, that are running under the hood, and they are always on. Even if you're processing 0 messages at this point, those polars are still up and running. Why? Because you're expecting a spike and you want predictable performance, right? Now, with provision polars, you're also getting faster scaling, and it's great for latency-sensitive workloads. So if you know that you're expecting a particular spike, you can have those provision polars configured within a few seconds. You will see it's literally just a configuration property, right? And we'll create under the hood those polars for you to accommodate your expected spikes. Now, in order to configure provision mode, this is what UI looks like. The infrastructure as code part is kind of very similar. You define the minimum number of event polars, and the default is 1. Right, so you cannot go lower than 1 because you're no longer using provision mode. And you can define maximum number of polars. You can go as high as 2,000, right? Now, my recommendation when you're evaluating this feature is start with 1 and see how much traffic it can handle for you, right? I have a link towards the end of this presentation in the QR code that you will see some data. For example, 1 provision polar can process up to 5 megabytes per second. So if you know your Kafka throughput, right, you know those bytes in, you can estimate how many provision polars you actually need for processing. And unlike traditional infrastructure, where with traditional infrastructure, you essentially have those provision polars, right? But scaling that up and down is extremely hard because that actually implies provisioning and deprovisioning infrastructure. With Lambda ESMs, it's literally a property. And we will take care of that for you. You can do it multiple times a day, multiple times an hour, okay? Now, to show you the performance difference, right? Because it's always interesting to see the numbers. This is the test case that I've implemented, okay? It's somewhat representative of kind of average, right, workload that I'm seeing. So the important parts are initial traffic is about 3,000 records per second. Traffic spike is about 9,000 records per second. We tested that with tens of thousands of records per second, but this is the workload that I've implemented here, right? You see the data for my MSK cluster, and in this test, I ran 5 provision polars. So my minimum number was set as 5. Now, first of all, let's take a look at how this looks with on-demand mode, not the provision mode, the default on-demand mode, right? So it's pretty self-explanatory and visual, right? So we start with 3,000 records per second, okay? Blue line represents published records, orange line represents consumed records. This is where spike is happening. This is where my traffic tripled, right? So the blue line went up. Orange is still not there, right? After about 7 minutes, right, the Lambda ESM made a decision, OK, we see a spike. We definitely need to scale up. So it scaled up a little bit above the blue line because we need to process the backlog, right? In those 7 minutes, a backlog was accumulated. So we need to scale up higher than the producing rate because we need to process that backlog. And after about 15 additional minutes, my blue line and orange line are back together, right? Essentially, consumption and production rate are back together at being good friends. So all in all, it took about 20 minutes, right, for realizing that spike has occurred and handling that spike, making sure that there are no records in the backlog. This is what it looks like in provision mode, right? You can barely see the blue line. It's actually there. Trust me, you'll see it once you zoom in the slides. It's there, but orange line essentially just hiding the blue line, right? Orange is just a little bit brighter, right? So in provision mode, since I have those polars already provisioned, they're up there, ready to process my data. So I don't need to wait for the scaling to occur. Now, if you've done Kafka processing, probably the question is in your mind right now is, OK, looks cool. What about offset lag? Can you show me what the offset lag look like? And yes, I definitely can. So this is the difference in offset lag, right? So you can see that the on-demand mode, right, essentially at peak had about 3 million messages in the backlog, right? And then it took some time to reduce that backlog. Those two charts are using the same scale. So at the peak for the provision mode, we had about 60,000 messages, which take about 5 to 6 seconds to process, right? So that backlog was tiny comparing to on-demand mode. In both cases, it was handled fully automatically, right? But in the first case, it took longer to handle it. In the second case, your workload, your end users probably haven't even noticed the delay, right? Because you had those polar provisions, and they handle the workload. Remember this? This is what I started with, right? So this is the spiky workload that I promised you to handle in the very beginning. When I see how provision polars handle that, pretty nicely, right? So those spikes, if you look at the numbers, this is about a little over 1K, and the largest spike is going as high as 7K, right? And those spikes are not happening in the span of hours. Those are within several minutes, right? So provision polar is handling that quite well. Now, provision polars can be used with other concurrency-related Lambda features like provision concurrency or reserved concurrency that work very nicely together. The pricing model is per hour charge, right? So we monitor for how long you use those provision polars, and the charge is per hour. And our documentation and pricing page, all of that is updated, right, with details that you can look at. So to wrap up this section, my recommendation is if you do have spiky workloads that cannot tolerate latency and you want predictable behavior, start exploring provision polars. Start with one. No need to over-provision right away because they scale super fast, right? You can change 1 to 2. Within a couple of minutes, you're done. OK, start with one. See how much a single provision polar can handle, and then set the minimum number to what you actually need, right? OK. So the last thing I want to cover today is observability, because this section is about monitoring as well. I showed you tons of metrics for the function. I showed you tons of metrics for the event source, like Kafka and Kinesis. But what about those event source mappings? How do you actually monitor those event source mappings? So for a long time, they were kind of a black box, right? And the magic was happening, but you didn't have a lot of insights about that magic. So once again, today I'm happy to announce that we've launched out-of-the-box ESM metrics, providing insights into the state of ingested messages. What it actually look like? It's a checkbox in Lambda configuration or a property in your infrastructure as code, right? Literally, that's the only thing you need to enable that. And what it looks like is when my ESM starts to pull data, I'm getting these two metrics, pulled event counts and invoked event counts. So you can see that they roughly match, right? Because those numbers are emitted once a minute, right? Aggregated at 60-minute intervals. So there is some, they're not fully overlapping, but they roughly match. So I can see that the number of pulled events right? Events or records or messages that ESM pulled from my data source is roughly equals to the number of events that were sent to the function that the function was invoked with. I got failed invoke count at the very bottom, right? I can see it's 0, right? Great, my function is working properly. And let's say at some point in time, I've introduced filtering because I saw this slide from Anton's presentation that talks about it can make your stuff cheaper and more efficient. And now this is what it looks like, right? So you can see that the polled event count is roughly the same. So the number of polled events is roughly the same, but the number of invoked events is now lower. By how much? Well, roughly, but the number of events that were filtered out. So now you can actually see how many events were filtered out, how many events were polled, how many events were processed. And all in all, there are 7 new metrics that are emitted from the Lambda function. Now, some of them are common to different data sources. Others are specific to data sources. For example, deleted event count is specific to SQS, right? Because for Kinesis and Dynamo, you don't really need to delete anything, right? But you have other metrics available for those event sources. And pricing-wise, there is no additional charge on the Lambda side, right? You're only charged on the CloudWatch metric side for those metrics, right? But on the Lambda side, there's no additional charge, right? So that's the reason that feature is opt-in, right? Because there is some charge on the CloudWatch metric side because metrics are emitted. We don't want you to start seeing additional charges and have no idea what that is, where that is coming from, okay? Once again, like I said, only charge for cost of metrics, duration, and CloudWatch. All the documentation and pricing page is updated, right? So I recommend you evaluate that. If you have ESMs running, enable it and see it right away. Okay. It's time to wrap up. We got about 5 minutes left, so I'm going to wrap up. If you have any questions after the session, I'll be right here. I'm more than happy to answer any questions, okay? So there are multiple techniques you can use for improving the throughput of your streaming workloads. Talking about Lambda side is process data in parallel. And this can be done at different perspectives. So Lambda concurrency, processing data with higher concurrency, and now you know how to increase that concurrency, for example, by using parallelization factor or by adding more partitions. Processing data in parallel will help you to improve the throughput. You can do this on the ESM level, right? Basically scaling out ESMs and processing data, having more execution environments. You can also look at how you do this within your function code, right? So if you're receiving a batch of 10 messages, maybe you can process those 10 messages one by one, but maybe we can process them in parallel, which will further improve your throughput. Reduce processing duration. I think that one is self-explanatory. The faster your code is, the faster throughput, the higher throughput is, right? You can either optimize your code, or you can try allocating more memory to your function because this will boost the CPU. If your function has higher CPU allocation, it might process data even faster, heavily dependent on what you're doing with that data in your function. Filter irrelevant messages out. I cannot stress how impactful that is. If you don't need to process the data, do not process the data. And I had customers telling me, come on, it only takes like 2 milliseconds to filter things out. Yeah, 2 milliseconds. Multiply that by 10 billion records a month that you're filtering out. Okay, so by using this very simple technique, essentially, you're throwing those redundant messages that you don't need out even before they hit your Lambda functions. Less invocations, right? Lower cost, higher throughput. Batch messages. Maybe you have a use case where you need to process those messages one by one, but most commonly I see that batching those messages and processing them in batches leads to significantly higher throughput and efficiency overall. And you have a lot of controls, what's the batch size, how long do I want to wait for that batch to be built, etc. And the last one is gracefully handle failures. Now, if your function is failing all the time, ESM can actually start scaling down, right? Because it detects that function is unable to process data, right? So in order to avoid that, handle failures gracefully in your Lambda function. Maybe send the data to failure destination instead of telling the event source that, hey, we'll throw in exception and telling event source that I just failed to process the data, right? So handle failures gracefully. On the event source type, Kinesis and Kafka, first, evenly distribute records with partition key. If you, use the same partition key for all the records, they will end up in a single partition, right? Or if your partition key is just not evenly distributed, you will have some hot partitions and cold partitions, basically partitions with a lot of data and partitions with a little bit of data. This will affect your throughput. If you evenly distributed records across partitions, your throughput will be higher. Buffer at the producer side. So this is an interesting technique. Instead of publishing those records one by one, you can also do some batching on the producer side, right? So if your records are not super large, you can send one record that contains multiple messages. So just like batching works on the Lambda side, you can also achieve that on the producer side, right? And this way you can also have additional throughput increase. Increase the number of partitions and shards where applicable. Right, so increasing the number of partition and shards usually comes with additional cost. So if you need to do that, yes, it's a great way to improve the throughput, right? But it needs to be a decision, right? That this is what I'm going to do to increase the throughput. Increased parallelization factor. This one is Kinesis specific. It's a single property that allows you to bump the concurrency, increase the concurrency. The number of polars remains the same, the number of shards remain the same, but concurrency suddenly double or triple or up to 10x higher, right? Use enhanced fan-out where applicable, also Kinesis specific. So if your workload, Kinesis workload, is very highly latency sensitive and you prefer to have it as push instead of pull, so lower latency, as low as 70 milliseconds, right? You can use the enhanced fan-out mode to achieve that. Now, fulfilling my promise, you can scan that QR code. Everything you've seen today, every single blog I talked about, documentation, including these slides, you can download it right now. Okay, everything is available to you. There are several more sessions I would highly recommend you attend if you want to learn more about serverless data processing, including getting some hands-on experience. So the SVS217, it actually was yesterday, right? But it will be on YouTube pretty soon, right? So we're recording all the breakouts. You will see them on YouTube. But there are additional sessions you can see there that help you to get deeper into this topic. So Chalk Talks, for example, I highly recommend. The SVS, which one? SVS 406. That's actually me and one more of my peers. And this is going to be a different format. It's not a presentation. It's just a discussion with the audience. That's what we call Chalk Talks. So I highly recommend you attend these sessions. Builder session. This is where you come and build. It's hands-on. You come and you're building Kafka workload with serverless capabilities, right? So also highly recommend to get your hands dirty and experience this on your own. Continuing your AWS serverless learning, right? So we have tons of enablement materials that you will find using this link. We have, the QR code that I showed you will link you to additional guides and workshops talking about serverless streaming as well. And earn AWS serverless badges to show your company, to show your friends on LinkedIn that you're actually expert in serverless. And with that, thank you so much. I hope this was useful. If you have any questions, I'll be right here in about 30 seconds. Thank you.